In chapter 3, we're going to take a look at how to use derivatives. And our first section here, we're going to look at extreme values. More specifically, we're going to utilize derivatives to find extreme values. When I say extreme values, what I mean is we are looking for the highest or the lowest point in a certain region. We look for sort of the top of the mountain, or we look for the low of the valley. That's what we mean by extreme values, the highest or the lowest point on a graph in a certain region. Now, we have to define it precisely. Here is our definition of minimum and maximum values. Let f be a function defined on an interval containing c. We say that f of c is the minimum of f on the interval if f of c is less than or equal to f of x for all x in the interval. That means it's the lowest point graphically. We say that f of c is a maximum on the interval if f of c is bigger than f of x for all x in I. And the minimums and the maximums are known as extreme values. We can also say that minimums and maximums are called extrema of f on our interval I. If we have a continuous function on a closed interval, then that function will have both a maximum and a minimum on the interval. Let me be specific here. When I said that f has a maximum and a minimum, there may be multiple points which are maximums and multiple points which are minimums. In other words, we could have the same outputs for multiple points. Let's take a look at example 1. Where are the extreme values for this f of x on the interval from 0 to 3? This is a closed interval. You can tell that by the set brackets. So it includes the number 0 and it includes the number 3. What I've done is I've graphed the function f of x equals x to the third minus 4x plus 3 in Desmos. We see the graph of this at any interval, but we can specify the interval from 0 to 3. If I do that, you can see how this goes. We see that my graph starts up here at the point 0, 3. Then it goes down to a certain low number here. And then it goes all the way up to this top number. The obvious graphical solution to this is that between 0 and 3, this point up here at the very top is going to be our maximum. And this point here at the very bottom is going to be our minimum. That means we just need to find out what those 2 points are. You can see that the maximum is going to happen at the value of 3. So we can find the maximum point or the maximum value by just plugging in 3. The minimum point happens somewhere here. Desmos is nice in that it highlights the minimum point and it also highlights the zeros. If I click on it, you can see the minimum point happens at 1.155, comma, negative 0.079. So there is the minimum point, and the maximum point happens when we plug in 3. Let's go ahead and do that. As we saw, the minimum point is this one here. If the minimum point is that one that we saw on our graph, that means the minimum value is the smallest y value. That's negative 0.079. We said the maximum point, which means the highest point, is going to happen with an x value of 3 on this closed interval. We can find the y value if we want by just plugging in 3 into our f of x. So plug in 3 into the function f of x, and I ended up with a maximum point of 3, 18. That implies that the maximum value is 18. You can see that the maximum value is always going to be the maximum output value. The same is true for the minimum value. It is the minimum output value. One of the downfalls of trying to use a graphing calculator to do these types of problems is that these points don't always come out precise. Obviously, our maximum value came out pretty precise. We could get that one. But this 1.155 is a rounded number. This 0.079 is a rounded number. If we wanted to be more precise, then we need to use some other method. And we're going to look at how derivatives can help us get maximums and minimums, which are very precise and we can algebraically solve for. That way, we don't have to rely on some computer algebra system to actually pick out the right point for us. And that's what we're going to do next.